Good morning, everyone. You know, it's terrible to be the last speaker before lunch, but to be the last speaker before lunch on the last day of the school is just the worst possible. So I'm afraid my jokes won't be up to what is needed this morning, especially after that lovely dinner last night. And I wanted to say how gratified I was to see all of you enthusiastically discussing the homework problem. Well, let's see how it goes. The helicity of the neutrino is my favorite past experiment in particle physics, and I'm aware that Concha has already exposed this elegant experiment to you, so maybe we don't need to discuss it too much, but I still might need some help from you since it's been 50 years since I took quantum mechanics, so a little help here and there would be much appreciated as we go through this, so don't be bashful. I also want to talk about Doom. Not working?
I don't think it is working, is it?
Yeah, let's see here.
Is it on? It's on.
No, it's not working. Hello, hello? Always this problem.
It's working. Now it's working.
Okay, very good. Okay. So, I'm not going to repeat what I just said. So, I mentioned yesterday that Dune is the flagship experiment in U.S. high-energy physics. So, we're going to talk about that because I think it might be possible to make it even better than it is now foreseen. And then here's an experiment that's right here at the LSC called NEXT, which stands for Neutrino Experiment Xenon TPC. And that's my favorite current experiment, so we're going to talk about that. Not only because I'm lazy and want to talk about something I know, I think it also has a great deal of instruction for us in the art of experiment. So let's see where to go. So this is the experiment that was used by Maurice Goldhaber, Luntens, and Sunyar way back in the 50s, where they actually managed to determine the helicity of the neutrino. Does anybody know what's going on here? Can anybody tell me what any of these parts are and what they do? Since you had lots of time to think about this and have heard about it before, I bet somebody knows what some of these parts are. Anybody want to tell me? Right. You all know, so I don't need to tell you. Come on, give me a little help here. What's this thing right here?
Lead.
What?
Lead.
Lead. Exactly. What's this thing up here? Magnet. Now what's this thing down here? It's a photomultiplier tube. We saw one of those yesterday. Here's an experiment with only one detector, namely this thing down here, and it is looking at something called sodium iodide, which is a scintillator, which has been around for a long time and is one of the most popular kinds of detectors where gamma rays are involved. Now these are rather conventional things: a photomultiplier, a piece of sodium iodide, and a piece of lead, and a magnet. But everything else is rather unusual in this experiment. So what is this thing here? Anybody know what that is? Come on, folks. What does that say right there? Yeah. Samarium oxide scatterer. And what is this thing up here? Europium-152. So what these guys did, and I'm going to say this wrong, I'm sure, so please feel free to correct me since you guys are all so smart. They made some of this Europium-152 by sticking the precursor into a nuclear reactor, and so this thing here is 50 millicuries of radioactivity. And of course it decays by turning into europium, from europium into samarium by a K-shell electron capture from the S wave. So it goes to from a 0 state to a angular momentum 1 state of samarium, and that decays by emitting a gamma ray, and that gamma ray can go anywhere, right? Let's imagine that we're going to only think about those gamma rays that happen to go in the direction of this detector or close to it. They have to pass through this magnetized iron to get there. So they can't get through the lead because it's just too strongly absorbent, but some of those gamma rays can come down here, and maybe some of them will scatter in this thing because that's what it's telling us it does. And the scattering is going to go everywhere, but maybe some of them are going to go into the sodium iodide. And what happens when a gamma ray goes into sodium iodide? Anybody know?
Scintillation?
What?
Scintillation?
Scintillation! We talked about that, exactly.
I have a question.
Yeah.
Is there this Sumerian scatterer thing? Is this significant that this is what European decays into?
Exactly, it exactly is. We're going to talk about that because that's part of the elegance of this whole thing. So the gamma rays that this Sumerian daughter is making are going everywhere, but we're only going to think about those gamma rays that come when the neutrino went upwards. Now when the neutrino went upwards, that Sumerian daughter is recoiling against that. The typical energy of that neutrino is about an MeV, right? You all read about that. So how much energy is that recoil nucleus carrying off? Anybody got a formula for that? Momentum, mass, like p squared over 2m. Ever heard of that? Okay, so what is that? Let's do the arithmetic in our heads. So we have a 1 MeV neutrino going that way, and this samarium nucleus weighs about 150 GeV. So if you do the math in your head, you get something like 1 part in 100,000 of P over M times the energy of the neutrino. So that's, you're starting out with 1 MeV and you're dividing it by 100,000, right? So this nucleus is recoiling downward in this case with only 10 electron volts, right? 10 to the 6 eV divided by 100,000. Did I get it right? That's 10 eV. That's not much. Should we ignore that, or is that important? Turns out it's critically important. So if the nucleus had decayed, or the European decayed with the neutrino going downward, the nucleus would have been going up, right? It's just simple kinematics. So if the neutrino were going up, the nucleus is going down, and it's going to give that gamma ray a little boost, right? I mean, it's a moving frame. It's not much, but, you know, we should do it right. So that gamma ray is going to get boosted, and those gamma rays go everywhere, but some of them are absorbed, and some of them go down here, and they run into some samarium here. They're coming from samarium with a little boost, and they're going to be absorbed by a samarium that's sitting still. So what happens in this case? I'm listening. We have a perfect energy match because the gamma ray hitting the nucleus is going to cause it to recoil with about the same momentum transfer. So the energy match is perfect. We got a little boost here, but we lost a little here, but overall the energy is matched, so we get what's known as a resonant excitation of the samarium down here. But we only get that if the nucleus was recoiling downward. If the nucleus was recoiling upward, we wouldn't have enough energy to recoil, to be absorbed resonantly by this nucleus. Because the energy of that state is pretty narrow. These nuclear states typically are maybe a few electron volts wide. But if we want to detect the direction of the motion of the nucleus, that gamma ray has to be emitted with an energy that's better than a few electron volts, right? Otherwise we won't get this resonant transfer. So now the gamma ray, and we're not going to do the quantum mechanics here, if the neutrino is going up with negative helicity, the gamma ray, because this is going from a zero state to a 1 state in momentum, that angular momentum of the daughter nucleus is also going to have the same negative helicity. And the gamma ray will carry that off as circular polarization. It's just carrying an angular momentum unit of 1. So the point here is that the neutrino going upward transfers its helicity to the decay product of the samarium, which is a gamma ray. This is extremely clever. He's not detecting the neutrino at all, but he's forcing the europium and samarium to carry that information into something that can be detected. Fiendishly clever. But that's not the whole story, because now this gamma ray has to come down here and be resonantly absorbed and rescattered. If it's not resonantly absorbed, which means a big cross-section, the gamma ray will pass through, and you won't see some of those gamma rays coming over here. So this is really cool. But the other thing that you have to know that this recoiling nucleus up here, if it stops before it finishes emitting that gamma ray, then this resonant fluorescence won't happen. So there's a very precise constraint on the nuclear state and the gamma ray that it emits. It has to live long enough to have a narrow energy state, but it has to decay quick enough before the nucleus here comes to a stop. So the upshot is that they had this europium decaying to samarium. The gamma rays were going everywhere. The nucleus was going up, going down, and sideways. But those gamma rays, rather the neutrinos that decayed upward, forcing the the nucleus to go down, emitted some gamma rays, and some of them hit here, and were resonantly absorbed and scattered around. And only if they were scattered here could they reach this detector here. So Goldhaber and company knew all this, and they did it, and it worked, and they found that the neutrino helicity, as measured by the circular polarization, because they could determine that by the scattering of magnetized electrons on the gamma rays, and it was more in one direction than the other. It's a tiny effect of 2%. So
wait, so they don't care about the polarization when they're actually measuring it. That information is lost in the rescattering, but it's just that the setup with the magnet
Yes.
forces only the circular.
yes, this is the magnetic. This is the polarization analyzer. It's just those electrons that are polarized by the magnetic field. So it's a weak effect, a few percent, and everything else is a few percent, because how many photons are going to hit this, and then how many of those are going to hit that. So they needed a rather intense source. 50 millicuries is a pretty husky source. So
this thing of having something that re-scatters and then a LED barrier is just to remove backgrounds, I guess?
that's right. You don't want those gamma rays to come down and overwhelm this, because they haven't been scattered. They haven't been shown to be produced by the nuclei that were coming down.
Okay.
If they could get here directly, it could be any gamma ray, whether the nucleus is recoiling upward, sideways, or down. So you have to only detect, if you can, those gamma rays that were at the precise energy from the resonance absorption and re-emission. So this is an example where nature really gave you something. Maybe europium and samarium didn't have to have this particular set of energy levels and lifetimes of the gamma rays, so that you could retain the information from the nuclear recoil and also sense it in this thing with a precision of like 1 electron out of 10 to the 6th. It's a beautiful experiment. So this is my best example in the art of experiment. Doesn't get any better than that, unless you guys can think of a better one. Okay. Any other questions about the helicity of the neutrino? Actually, as it was noted in, not at the time but later, they didn't really prove that the neutrino was fully negative helicity. It could have a right-handed component, because the precision of that experiment was -1 plus or minus 0.2 or something like that. So there's a lot of room for B plus A, but nobody thought about it at the time. Anyway, this is not about that, it's about experiments. So I'd like to move on to something called Dune. So these cartoons show a 10 kiloton thing with people looking at it here. This is kind of a cutaway view. 10,000 tons of liquid argon in a TPC configuration to really characterize the properties of neutrinos after traveling from Fermilab to South Dakota. So the way it works is there's detection planes here and cathode planes here, so that any ionization in these volumes are drifted over to these blue planes here, which are wrapped wires. There's a vertical wire, and then there's 2 other wire planes running at an angle to try to reconstruct what really happened. Now, we talked yesterday about what happens when you have spatial projections. Although the multi-wire proportional chamber revolutionized the field because it could not only produce very precise trajectories, but it could be triggered, and it ran at very high rates, it didn't solve the issue of complex events. And ideas like the time projection chamber managed to do that. So here we are once again with the problem of spatial ambiguities and event reconstruction. So the TPC works, as you know, according to this cartoon. You see the signals arriving on the wires, the collection wires, and these are unipolar signals. However, as the charges float past these wires at angles, they initially induce signals, and then as the charges move past, they induce signals of the opposite polarity. So these signals look like derivatives of the current, right? Down here you're seeing the current pulse. And up here you're not really collecting the charge, you're seeing the derivative of the current as those lumps of charge pass nearby and then move away. Okay? So to really reconstruct what's really going on here, you have to integrate that twice to get the charge, whereas down here you only have to integrate it once to get the charge that was actually delivered from that track. So the double integration, in a practical sense, tends to introduce much more noise because there's electronic noise and so on. So this works, but it's a little bit complicated because of the fact that these are derivatives of the signal rather than the signal itself. Now the reason, or I should say the approach then is taken now is that one is looking at these wires all the time with digitizers. Maybe every microsecond you say, well, what's this signal there? I'll digitize it and I'll look at that number, and if it's above a certain number I'll call that a signal. So the thresholds are digital now these days. But you're very busy. Every one of these things is working all the time to see if there's any signal. That's not really bad, but it costs you power. All of this stuff is going to be immersed in liquid argon. And another aspect about the Dune project is that most of the time, almost all the time, nothing happens. But let's look first at what those tracks might look like. Here's a complicated event, the Monte Carlo event, in which something comes in and there's electromagnetic components which cause showers. You can see all these little spots. This is the so-called Monte Carlo truth. Now, when the tracks overlap in time, you cannot really reconstruct those or disambiguate the event, so it looks like a mess. However, you can try to correlate the charge on the wires to say, well, that big charge corresponds with this set of wires, and that small charge corresponds to that one. And you can see that there's quite a bit of improvement here. But overall, it's not great, because when Dune is done, there's only going to be a few dozens of events in some important channels. Every one of those events is worth millions and millions of dollars, and you don't want to have bad events mixed in with the good ones, because that will directly contaminate the systematic error of the experiment. So, what to do? There's a lot of work trying to improve the algorithmic development here, but you still can't get there. You simply cannot completely disambiguate things, and so I view this activity, which is very sophisticated, as basically putting lipstick on a pig. And I don't get many free beers from the Dune management when I say things like that, but I think it's true. Okay. So one of the most important things is not to confuse some electromagnetic element with an electron that really was, you thought came from a neutrino, but really was some other kind of hadronic interaction of the neutrinos. This is a particularly lethal kind of confusion, and so you'd like to have highly accurate and highly detailed reconstruction. At the same time, there's a lot of activity going on, and before Dune is done, the mass ordering, which is one of its goals, is likely to be pretty well determined. It's already more or less at the 2 sigma level. We'll talk about what the mass ordering means if that doesn't be clear right now. Some of the other goals are to wait for supernova and to try to see what is actually happening in both the development of time. If the supernovas in the galaxy, we'll see very lovely time dependence of the neutrino signal. Another thing to do is to wait for nucleon decay, but you may have to wait a long time for these. So one can return then to the fundamental idea of the TPC, which is to give yourself intrinsically three-dimensional data. So why corrupt it with some kind of technique that doesn't really do that? So as a slogan, you can say to yourself, I want to optimize Dune and make it a true discovery machine so that if there's anything there at the threshold detection, we don't know what that might be, but we want to get all of the information as accurately and as detailed as we can. So from this perspective, one can start to think about Dune in a new way, I claim. First of all, the information quality is extremely high in these devices because the information arrives rather quickly. The electron signal moves through the liquid argon at about 1 millimeter per microsecond, similar to what it does in the gas phase. Remarkable due to the similarity of the liquid noble gases to semiconductors. So it can arrive after meters of drift with 2 or 3 or 4 millimeters of diffusion. That's really excellent. You'd like to have a very low threshold because everybody knows that there could be a lot of physics down right where you don't see much in terms of energy transfer. Don't know what that is. You could imagine things, and again, imagination may be more important here than knowledge. Maybe there's a wave of axion-like particles flashing through your detector, giving you tiny little energy losses that if you had a digital threshold too high, you wouldn't see it at all. So you want to have as low a threshold as you can somehow. At the same time, in these huge detectors, there's something like 10 to the 12th addressable voxels, volume elements inside these big detectors. That's a big number. And again, nothing is happening. So you have to think about some kind of equivalent of the least action principle, which we learned about in mechanics. But here we might think about that in analogy in how to design a detector. Okay, so from this kind of perspective, we can try to imagine how might Dune be better. So there's now an activity called QPIX, which I'm going to tell you about, and since I have a captive audience, you're going to hear all about it. And its aspiration is to completely pixelize the far detectors of Dune. Now we're talking about hundreds of square meters of detector that have little pixels on it, and that seems like it's way more complication than you would like. But maybe not. Let's see where this goes. Now, we know that there's going to be an unorthodox solution for this because of the immense scale of these new Dune far detectors. I just told you that the way it's done now is to measure how much charge you're getting every microsecond, charge per unit time. These are clock-driven data acquisition, so every microsecond you see, did I get something? Okay, no. And you do this, a million times a second, you say, no, I didn't get anything. It appears that something has been overlooked because current, which is what the interesting thing is just amount of charge per unit time. So instead, you can measure time to a certain amount of charge. As far as I know, this has been completely overlooked until now, and yet there's no reason why this shouldn't give you equivalent information. How does this help us? It's, I think, a new way to capture complex waveforms with high resolution. In particular, the small energy deposits are going to be captured with the highest resolution, unlike the conventional solution, which measures charge per unit time, where small charges don't have as many bits. Okay, so another thing you need, if you're going to do things in Dune, you have to have extremely high resilience against something like single point failure.
Can you explain what is time to charge, please?
Yes, I will do so.
Okay.
That's the next 40 slides.
Okay.
Wow, not really. Yeah, you're going to see that. But you have to also think about the fact that if you're going to put all this stuff in liquid argon, you might as well be putting it in the moon because you're never going to drain these detectors of their liquid argon to fix anything. So once it's embedded in the liquid argon, and that's true for the conventionals, you're never going to touch it again. So what you want to make sure of is that if something breaks, a wire, a chip, a circuit, whatever, it doesn't disable your detector. It just has the minimal effect. This is what's known as single point failure, we've seen this in an unfortunately terribly graphic way with the Boeing 737 MAX, in which, for reasons that astonish people who are familiar with engineering, they had a software system that pointed the nose down if one of the attitude sensors said that it was too steep. So one device could cause the plane to go down even if the device was incorrect. And this is what has happened apparently. Hundreds of people have died because of this. Everybody knows you don't do that.
Sensor, wasn't just one sensor? They had
What?
only one sensor.
Yes, that's what I'm saying. One sensor. They had two, but this system would go into action if one of them said that the plane was climbing too steeply, and it would try to point the nose down even if the plane was flying horizontally. That's a graphic example of an engineering failure against single point failure. Okay. So if you design things properly, you can also do this in a way that I'm going to explain. And it also allows you to, if you do this properly, you can put maximal functional devolution. What I mean by that, almost everything occurs right there where you're sensing it. You saw this in the Auger project, and you saw this also in IceCube. But another thing you can do is to exploit argon-39 decays, which is made in the atmosphere by cosmic rays. It decays with a long enough lifetime that it's producing continuous current inside the detector. So you can use this in the QPIC scenario to give automatic absolute charge energy calibration of your system. Okay, so what is this? Now we are going to delve deeply down into the electronic domain. Has anybody seen any kind of circuits like this? Is this completely new? Who's seen a circuit that looks like this? Anybody? Nobody. Completely new, right? Did I see a hand? Okay, we're going to start at the basics. And this is useful, I think. What is this? Well, these triangles in electronic speak are typically amplifiers. Now here's another triangle, but it's got this symbol in it. This means that it's a regenerative comparator. It's not really an amplifier in the usual sense. I'm going to tell you what that does. So we have two things. We have this amplifier thing and this S thing, which is known as a Schmidt trigger, also known as a regenerative comparator. So now what this amplifier is doing, it's looking at this input. And if charge is appearing here, it's going to try to raise the voltage on this node, but the amplifier won't tolerate that. So what it does is it puts charge on this capacitor here so that the input voltage is always maintained, let's say, at 0. So the net effect is if I'm putting charge here, it's going to wind up sitting on this capacitor. So this is what's known as a charge-sensitive amplifier. These are everywhere in modern electronics. So charge coming in, whether it's slow or whether it's fast, is going to wind up on this capacitor here. Now this thing up here is just a transistor which shorts out the charge if I turn this switch on. And that switch is turned on if this thing here says, oh, the voltage at this point, which is due to the charge sitting on this capacitor, has reached a point where I'm going to switch. In other words, this thing has either an on or an off output. This has a proportional output depending on what it gets in. This is either on or off. So when the voltage rises here to the point where this switches, boom, it goes up here, takes all the charge away, and then everything goes back to 0. And all you get from this circuit is that something happened, right? But you know that it happened only when this got to be a certain charge, because this threshold is related to that threshold voltage. You know this capacitance, and so you know how much charge was integrated, right? Really simple, right? Okay? So now what do you do with this? All you do is you measure when that happened. So there's a clock that's running, say, at 50 or 100 megahertz, just producing little ticks. And this is a thing that counts it up to, say, like 32 bits. That's a few seconds or a minute or something like that, depending on. And all that happens is when this gives you a signal, is you store that and put it in some kind of memory. So the only thing that's happening now is that you record the time when something happened. And you know that when something happened, a certain amount of charge was reached on that integrating capacitor. And there's some other stuff. You have to know which integrated circuit that was, which pixel that was within the circuit, and so on, but you don't need to worry about that. So what's new here is you can measure current by looking at the difference between these resets. So you get this string of resets from each of these circuits. And the time can vary quite a bit. It depends on how much current was coming in. So the basic quantum of information is not one of those resets, but the difference between the two sequential resets, which means that you got that much charge between those two times. These are not generated, these reset time differences. They're generated off the detector nearby in some kind of small computer system. So the reset time differences capture the waveform. They measure the instantaneous current so that if the current is small, you're going to get a large difference between the reset times. Now the argon-39 generates about 100 attoamperes. 1 attoampere is 6 electrons per second, so that's not very much current. But if you have a large input signal, the difference between reset times can be very small. Typical track current from a muon in liquid argon might give you 1.5 nanoamps. And so the signal, the background here, namely the RTD when you have a real track versus the RTD when you have just background current, is like 10 to the 7th. So these are easy to distinguish. So background, there's going to be seconds between the reset times, and in a signal case, you're going to have microseconds or fractions of a microsecond. So this is how we're measuring current now, by measuring the time difference rather than the current per unit time. Just delta Q over delta T, where here we let Q be fixed and we let delta T vary. So Pilar, am I getting through? So when you think about it, it's really very simple, but as far as I can tell, nobody's ever tried to do this. Okay, I've said this several ways. But we have to choose our delta Q so that we will see these minimum ionizing tracks. In fact, we want to set that so that we see the entire profile of the track so that it will give us what the diffusion is and help us determine how far it has drifted. So something like 7/10 of a femtocoulomb seems to be about right. That corresponds to like 120 kilovolts of energy loss in the liquid argon. Okay, so we can reconstruct any waveform, arbitrary complexity, from the sequence of RTDs, just as we could do it. So let me draw your attention to this purple curve down here. This is from a simulation where these spots come from X-rays, gamma rays. And here's a track profile coming in at an angle into a mythical pixel. And you can see that it's very jagged due to the fact that the ADX is a very jagged process. And here we see that we don't see anything until we reach delta Q, and then we measure things pretty well, and then we lose it again. So maybe 1 femtocoulomb is a bit too coarse. Let's reduce the threshold. What's happening here is the green lines are when the Schmidt trigger registers, and that you can see that they get shorter when the current is higher. If you reduce that delta Q down to 3/10 of a femtocoulomb, and remember 1 femtocoulomb is 6,000 electrons, it looks a little too busy and it's maybe overdone. So somewhere around 7/10 of a femtocoulomb might be about right. So we're getting heartbeats from each of these pixels about every 10 seconds when the argon gives us enough. There could be other background in the detector from just radioactivity in the components. But something like seconds for the heartbeat, that tells you that the pixel is alive, and also gives you some sense of automatic calibration. Okay, so there's no signal differentiation here, unlike those induction wires I criticized earlier. You're also getting current from negative ions, so even if the electrons are captured by contaminants like oxygen floating around in the liquid argon, you'll see that charge too. So it really is using all of the argon-39, which is a guaranteed free signal. However, I mentioned that the first trigger and the last trigger is maybe not so well defined. Perhaps corrections are possible, but I wanted to point out that it's not perfect. But I wanted to point out that QPICs has hundreds of tons of liquid argon with nearly zero threshold, because the liquid argon, the argon-39 is continuously raising the threshold to where it's almost zero. So it's quite sensitive to small energy deposition. We don't know whether that's going to be useful or not. But the point here is that this stretches our imagination. Nobody's done this before. We don't really know if it's going to give us any new physics, but maybe it will. So it might look something like this in implementation. Here's an application-specific integrated circuit that has 16 pixels. Pixels are not likely to be these white squares. They're more likely to be little bumps, but this gives you the general idea. There might be 32 or 48 pixels in one ASIC, but for just conceptual, you would imagine that there's pixels that reach to like 4 by 4 square millimeters.
Dave, can I ask you?
Yeah.
Do you think it would have some dead time? So how fast can these resets occur? If you have a
Well,
heavily ionizing particle, are you going to miss some of these resets, or that would be a problem?
I think that the real answer isn't known, but we've thought about that, and that reset transistor can be set so that it always removes exactly delta Q. This is somewhat idealized. So if a huge amount of charge comes, it would continue this, eat down that huge amount of charge and measure it over a certain period of time, but you'd measure the charge accurately, stretched out a bit, but you'd know that because you're getting all of these consecutive resets. Now the other side of the question is, why do you care about those big energy losses? At some point, they're just nuclear fragments. Maybe they're coming from proton decay inside an argon nucleus. But those are going to be messy.
But you do want to measure, for example, the neutrons that gives you off
Right.
protons.
Yes, those are going to be seen okay. It's when you get these hugely ionizing nuclear fragments that it gets hard for anybody. It's a good point. I mean, we have not simulated this to the point where we can give you a good qualitative answer, but we are concerned that, well, we think it's probably manageable. So the basic thing you'd work with is maybe a tile that's like 25 centimeters by 25 centimeters with a number of pixel chips like this. And one important thing about this cartoon is that there's nothing else other than these ASICs here. There's no other layers, and I'm going to talk about that a little bit more. So the question is, how do you actually measure the time? Each of those ASICs has a clock running all by itself, and there's no phase lock loop here, so it's again like Ice Cube. Everything is self-contained. You don't need to have a lot of communications going on all the time with the outside world. The requirement here is that the local clock should be stable to about 1 part in a million, whereas Ice Cube needed it to be 1 part in a billion, because there it was nanoseconds. Here we care about microseconds. So you can just do this simple interrogation about once a second, ask each ASIC what time is it, it stores that, and then you send it out and do your transformation. So you know that I mentioned a moment ago that it's Ice Cube, so this is a reincarnation of that basic idea. Now, it's probably easy to get this precision immersed in liquid argon. We got it in Ice Cube by paying a lot for a very well-constructed quartz oscillator. But the point is that once it was shown to work, everybody forgot about it. It just is part of the wallpaper now. And so now we're not going to have something as complicated as this, but we're going to have the same functionality where a signal comes in and eventually packets of stuff come out that are time-stamped, at least in the local. So the QPix is going to become a system on a chip. Not as complicated as this, hopefully, but it will store all of the hits in its own time frame, and once a second it will be asked to push out the data where you can deal with it. So here's this cartoon again. What happens if one of those ASICs goes bad? Now we don't like that, because if that one ASIC stops all the rest of them from reading out, then you have a problem. You have not designed your system properly. So the solution here is that each of these ASICs can talk to its nearest neighbors, its 4 nearest neighbors, and it can decide, how to talk to the nearest neighbor, the one on top, the next to the right. So it will find its way around so that if there's a dead one, it will find its way around, and only if it's like a game of Go where you've managed to get a bunch of bad ASICs, it seals off a section. Only then would you lose the ASICs that are good. So this dynamic network generation is new to particle physics, but it's something that the experts do in networks all the time. So we're just introducing something here that is not really novel, but it was not something that has been characteristically done in particle physics. Okay, I've mentioned this already. You ask it somewhere on the tile periphery, and it sends it, offers it to all its neighbors and so on, and then it pushes out all the data. So this is one good way to get resilience against that single point failure problem. There's no master clock distribution, and the architecture, as the electronic people would say, is flat. There's only one layer. There's not a bunch of layers, where the higher layers, if they fail, you lose everything below it. Okay, so in cartoons you could start at this corner, or really anywhere in the periphery and say, give me all your data, and presumably the network would work it out and send it to you. So QPIX kind of stretches our imagination. Now, I don't need to talk about this. There's not much data that comes out because normally not much is happening. Now, the central technical issues of QPIX are that you would like all of the leakage currents inside that circuit I showed you to be tiny compared to this argon 39 current. We have to test that in liquid argon with realistic chips, and that's something we plan to do. Also, there can't be surface charge creeping around on the actual pixel surface itself because there's electric fields in the argon that may build up charge in a way that could lead to discharges and so on. So we don't know about that either. And we know that the clock has to be stable to something like a part per million, and we think that will be easy. So those are the technical issues that we are going to be addressing. So it's necessary to place all this in context. Dan Dwyer at LBL has been working on something called LARPIX, and he and his collaborators at UTA and Bern, Switzerland, have been doing this for a while. They have developed chips that are shown to work pretty well and will be the choice for the near detector. He also made a cost estimate showed that these costs of silicon actually are not so great. There are hundreds of square meters of silicon now in particle physics detectors around the world, even in calorimeters. It's cheap because if you can stay away from the cutting edge technology, it's quite inexpensive. So the idea has been, of QPIX has been sufficiently appealing that there's now a collaboration that wants to develop it. In fact, the program manager at DOE basically said, well, aren't you going to propose this so I can give you some money? So we actually have now $700,000 this year to try to get going on this idea, even though we have no connection officially to the Dune project. So this is another interesting aspect. So we are like the Chihuahua biting at the ankles of the St. Bernard. We'll see how it goes. I've seen this before where it looks like nothing is happening, but if we get to some point where, hey, you know, it looks like this stuff works, looks like it's not so expensive, why not do it? We don't know when that point will come. We don't know if it will come. But I think that we need to recognize that Dune is not an optimal experiment. It may be missing some of the capability it has intrinsically, and maybe QPIX will allow us to get there. So already IceCube shows that you can make these radical steps and have complex electronics embedded in perpetuity if you know how to design properly. We avoided super high-speed clocks in IceCube, only 10 megahertz. You had to take great care in picking your parts, and then you had to know who was fabricating all of your boards. And that worked so well that we couldn't break them in the IceCube testing. We spent a lot of money testing these things, cooling them, heating them, shaking them, couldn't break them. So we know that this can be done. And so yesterday's high-risk approach is today's, it's obvious. Okay, so QPIX extracts the energy and the spatial and time information with adequately high precision, great detail and appropriate dynamic range, although I don't think Michelle believes me yet. That's okay. Whoops. apparently there's something new here to exploit time to charge rather than charge per unit time. So it's possible that if we actually manage to do this, we're working also quite collaboratively with Dan Dwyer, and maybe our ideas will help him in his approach to pixelizing the near detector. Maybe we will find something, and we're really doing Dune only for that. We want new physics. We don't just want the things that are on the menu right now. So this is our real goal, to make sure that we discover any new physics that they're near the threshold of detection. So that's QPIX, and the reason I dwell on this is partly because I'm lazy. I can talk about something I know more easily than something I don't. But it also stretches our imagination. Why in hell did nobody ever talk about measuring time to charge rather than time per charge per unit time? So I want you to carry away that not all the advances have been thought out. This is not necessarily the best idea, but it's an idea, and this is how we reach one punctuated equilibria from another. Yes, I've already mentioned this. We don't know whether it will be a genuine advance or an amusing detour, but the people who are in the collaboration are willing to take that risk. Okay, now, let me see. Okay, I'm good. Hang on a second. I'm going to switch now to the topic of double beta decay. Maria Guppert-Meyer and others in the 30s showed that double beta decay could occur, even possibly without the emission of neutrinos. And over the last half century or so, searches have been increasingly sensitive, but there's no definitive result to show that neutrinoless double beta decay exists. And now it has become our turn to search. So double beta decay is an allowed, rare process where you have the case where one nucleon decays into an electron and antineutrino, another one simultaneously. That's what makes it rare, as a second order radioactive decay, and it's only seen for those even nuclei for which the next on the periodic table lies above in energy, so that a direct decay is not possible, but a double beta decay can bring you to the lowest energy state, in this case xenon to barium. One can also see from this diagram that cerium could double positron decay, but not to lanthanum. And there are other decays that can occur as well, but this is the one that I want to discuss today. What you look for as well is those nuclei where there's a big energy difference between the parent and daughter, because that gives you a big boost in the expected rate. In the case of neutrinoless double beta decay, this neutrino that's emitted here has to be absorbed here, and this can occur if the neutrino and the antineutrino are identical, whether a neutrino leaving is the same as an antineutrino coming, and this would violate lepton number, and it could also be mediated by any dozens of theoretical processes. I certainly am not going to try to talk about them today, but what's of interest is that the allowed process is already 1 million times the age of the universe, 1 billion times the age, something like that, almost 1 billion times the age of the universe. So this means that you're going to have a lot of nuclei even to see the allowed process. The rate for the sought process of great interest is the product of a phase space factor, which is based mainly on the energy difference between parent and daughter, complicated evaluations of the nuclear matrix element between parent and daughter through all the intermediate steps, and then the so-called Majorana mass term. The most interesting candidates are those with a large difference called Q between the parent and daughter. Calcium-48 is probably the most prominent, but the most difficult, since it's very hard to get hold of. Its natural abundance is very rare. Germanium is very popular. Selenium has been popular. Molybdenum is another candidate because it has a high Q value above most of the troublesome radioactive sources like bismuth-214 and thallium-208, and so on. And here is xenon-136, has a high natural abundance, but Q value that's unfortunately just a little bit lower than you would like, but not fatally. So the popular ones are germanium, selenium. Sometimes people look at for zirconium, molybdenum, but these are hard to enrich rather. Tellurium is popular too because it has such a high natural abundance. People also consider neodymium because it has this high Q value. And the phase-space factor differs a lot, even though germanium has a low one because its Q value is low. It's still been very popular because of the instrumental opportunities in high purity germanium diodes giving good energy resolution. Okay, so the menu is quite large here. The calculation of the nuclear matrix elements varies a lot depending on the model that people assume, whether energy density functional interacting boson model, shell model, and so on. And so these these errors or uncertainties come as the square. So you have to be brave if you're going to imagine it. The matrix element is that low where you'd hopefully be that high because it comes in as the rate comes in as the square. And xenon also has a very large range and a possible value of the nuclear matrix element. So that's another source of uncertainty. The last term, the so-called Majorana mass term, is a sum over all of the neutrino mass states, leading to this complicated expression involving the mixing angles, phases that only occur in the double beta decay. And all of this leads to uncertainties, also including whether you know the absolute values of the masses and the mass differences. So we don't know the absolute mass of the neutrino. We know something about the mass differences, but we don't know whether it's the so-called normal mass ordering or the inverted mass ordering, but it seems to be favored to be the normal one. So there are a lot of uncertainties, but that does not stop people from trying. Another way to look at that, as a function of the lightest neutrino mass state, you can get serious cancellations here, which make it experimentally inaccessible. For the normal mass ordering shown in red, the inverted one is more appealing experimentally because it has this minimum, and one could hopefully push the sensitivity from where it is now down below this and make a positive statement of possibly whether the neutrino is antineutrino or mass or normal. Sorry, Majorana or not Majorana. Okay, so there's a lot of uncertainties, both from the unknown neutrino parameters and from the nuclear matrix elements. So what this means, if you want to get there, you need about 2 tons years of xenon exposure with no background, 1.5 tons of neodymium, selenium or tellurium, or 3 tons of germanium. So you get an idea of how difficult this experiment is. There are dozens of ways that one might have neutrinos double beta decay, but one popular one is leptogenesis, which invokes the existence of heavy right-handed neutrinos that would force a Majorana mass term, forcing the neutrinos to be neither matter nor antimatter. And only neutrinos could be Majorana in the standard model. Interestingly, the leptogenesis predicts that the leftover baryons relative to the annihilation products in the early universe is what is observed, which is quite remarkable. And it also predicts through the seesaw mechanism that the mass of the neutrinos will be a few tens of millielectron volts, which is also what the oscillation experiments indicate. And of course, the neutrino mass is 1,000,000 times less than the electron mass, so it's clear that there's some new process that's generating that mass. So it's a very appealing one, but it's only one of many. And it's part of the motivation, I think, that leads people to think that this is worth searching for. So the ideal result experimentally would show the 2 neutrino decays where the neutrinos carry off a fair fraction of the momentum and energy. And here at the Q value would be a delta function where there would be only neutrino decays. This spectrum actually reaches to that point with vanishingly small intensity. But if your resolution is poor, this spectrum can invade that region and complicate the detection. And of course you would like to have no backgrounds anywhere. So that's what you'd like to have. In practice, one will have experimental resolution. If you had 5% energy resolution full width at max, and the rate was 1% compared to that, you'd see this bump and that'd be easy. But if it's only 1 part in a million, it would just look as a shoulder to this spectrum coasting down to the Q value. So energy resolution is one of the things you absolutely must have, and it appears that you need at a minimum of 2% full width, but really 1% is better because you never know for sure whether your energy resolution follows a Gaussian or some other more complicated shape. So let's look at what the energy resolution does if you have background. And so if you have 0.5% full width for a reasonable choice of neutrino mass and a rather substantial exposure with backgrounds of 1 count per kilovolt in the region of interest per ton per year, you would see that peak very clearly. When you get to 1% full width instead of a half, it's still pretty clear. When you get to 3 or 4%, it's really not much, and 10%, which is characteristic of some of the detectors that have been built, you can't see it at all. So clearly I'm hammering on the question of backgrounds because that really is whether you win or lose in this game. If you have backgrounds, your sensitivity to this only rises as the 1/4 power of the running time, and after a while you run out of willing graduate students to run the experiment. So this is really a brick wall. Another way to express this is to look at what happens as a function of exposure. Here's 1 ton year. You can assume different backgrounds. We have none, 1/10 of a count in your region of interest per ton year, and so on up to 10 counts. And you see if you have lots of background, you have to run for 1,000 years to get all the way through the inverted mass ordering. As you can see, now we're trying to go vertically in this scale. So it's a killer to have background. You really have to try to get rid of it. Even at 1/10 of a count in your region of interest, you have to run instead of 1 ton year, you have to run for 10 ton years, or I should say a couple ton years. So this is another way to understand how we really need to run our experiment. The Nuclear Science Advisory Committee said, let's have a ton-scale US-led experiment. But they didn't say anything more about where, when, who, or how it would be done. But they set the scale now for a competition in the US to actually build a ton-scale experiment. But they also said that the common goal should be 0.1 count per ton of isotope per year in the region of interest. And you saw a couple of slides ago that even with 1/10 of a count, you're already losing relative to a truly background-free experiment. So B is the background index, typically given as counts per keV per ton per year. And delta E depends on your resolution in your experiment. So you need to multiply these two things together and get a value that's less than this to match the goal of the NSAC committee. Now, to get a sense of how difficult that is, you just take 1 kilogram of your detector and put it in your counter and count for 100,000 years. And if you did that, you would be able to show that 1 kilogram shows that your detector would be at this level. So that's illustrative of how difficult it's becoming. Nevertheless, there's lots of contenders. Kamla and Zen is leading in a sense because they have so much mass, even though their energy resolution is not so great. I'm not going to spend much time discussing this long list, but just to show that there's a lot of people who are trying to do this. 2 experiments in particular, Gerda and Majorana, have joined to become legend with 200 kilograms and quite possibly more if the US invests as well. EXO was a very successful experiment. They plan, if they're selected, to go to 5 tons of a particular isotope. And the WIMP search experiments are also trying to establish a way to see these relatively high energy events and also produce a limit or discovery. And so on. Now, next is an unusual one in that it's a high pressure xenon gas TPC in an advanced R&D stage. I don't really have time to go over all of these, although they're interesting in their diversity. So the results are that Camlins then had lots of background. They have less now. EXO 200 had lots of background. And everybody has to go down toward this in order to really meet the goal. This is our prediction. We don't have a measurement yet for the 100 kilogram system that's going to be built. But you can see that we're a long way from this 0.1 counts per ton year in the region of interest. Now, we don't live in a logarithmic space. It doesn't look so hard when it's projected on a logarithmic scale, but when it's projected on the scale in which we live, namely the linear scale, all of that goal is way down here, and you just really can't even see it. So it's going to be a challenge. So I'm hammering away on the background, and I want to get there soon for what we want to do about it. Over the past half-decade or so, there was a steady improvement in the limit that the people were able to do, and then it's gotten harder for the reasons that I mentioned. The experiments are getting big, and it's getting very hard to know in advance that you've achieved the background index you want. There's 4 general approaches to background rejection. Have the best possible energy resolution so that most of those background events don't fall into your region of interest. Of course, you have to make sure that you make your detector out of the most pure materials and shield it from background gammas from the laboratory. And typically all of this is done deeply underground to avoid the contamination from cosmic muons. In some experiments, you can actually look for the 2-electron topology. That helps to get rid of the events generated by gamma rays, which generally generate only 1 electron. Another way is to look for the decay daughter, because the gamma rays cannot, or the alpha particles, whatever, generally do not turn 1 nucleus into a nucleus with Z plus 2. So in NEXT we concentrate as well as on the top 2, but the second, the third and fourth as well. Xenon itself is a fascinating isotope because, first of all, it's not radioactive, it has a high natural abundance, it's easy to enrich, and already about a ton of this stuff exists around the world in various experiments. But there's an important difference between liquid xenon and gas, and that has to do with partition fluctuations in the energy. In the liquid, one sees very large fluctuations between ionization and scintillation for a constant energy deposition. And they're small in the gaseous state, and this is shown in this slide here, which is a truly revolutionary plot. This was shown in 1997. What's shown here is the density of xenon in grams per cubic centimeter. What's shown on this axis is the energy resolution in a setup where they were measuring the energy resolution for a gamma ray of 660 keV from xenon. And down at relatively low densities, the energy resolution was what you expected, 0.6% full width. However, as the density increased, the resolution began to deteriorate and probably reached something like this, which is 7%, whereas about a factor of 11 worse than this at the liquid state. So this is weird. Can anybody guess what's going on in this plot? Why would there be a transition when the density is about 0.5 gram per cubic centimeter, and gradually getting worse and worse until it reaches a value which is 11 times worse than in the gaseous state? And this is measuring only the ionization signal. Presumably there was a lot of energy going into the scintillation that was not measured here. So this is why the resolution can be so much worse. The partition fluctuations between scintillation and ionization. Anybody have the faintest idea what's going on here? I mean, this is weird, right? How can this be? Well, I think that the one good answer is that nobody really knows what's going on here. But one can get some clue from the fact that the critical temperature of xenon is room temperature. So as we're going up in density here, we're starting to develop droplets of xenon, evanescent droplets that form and then go away. And there's more and more of it until finally you get full liquid state. So the prevailing idea is that as we go above 0.5 gram, the presence of the liquid state is sufficiently high and increasing that whatever is going on in the liquid state is causing these fluctuations. So that may explain part of it here, why there's a sudden onset and then a steady decrease in the resolution until you reach that.
But why is it basically flat before that, right? Because this, I mean, that argument would just imply it's uniform.
Well, down here, I'm going to talk about what this means down here, and that's an interesting story in itself, so let me hold off on that. But presumably what's happening down here is that the presence of the liquid state is sufficiently small so that it doesn't control the resolution, that it's the intrinsic fluctuations that are controlling it in this region here. So anyway, we thought, this is interesting to try to work in this region because it's very difficult to measure all of the scintillation signal. Those photons go everywhere, and there's not so many of them in the primary scintillation, so it's possible to make some compensation by measuring the scintillation signal as well. And this is what EXO has done, and what NEXO would do as well. But here we can not have that complication. We can presumably get intrinsic resolution or close to it. Now this is only at an energy that is 1/4 of the Q value of xenon decay. This was the cesium gamma ray at 662. So this was the plot that started the next project back when it was noticed a few years after this publication. So let's look at what's going on in the xenon. So we know that the difference between the xenon and the barium daughter is precisely known, 2,457 keV. We also know that it takes something like 25 electron volts to make an ion pair, an electron-ion pair in gaseous xenon. That number depends on the density, and it also depends on the electric field, because there is a process called geminate recombination where you may ionize a xenon atom, but that electron is sufficiently close that the xenon ion recaptures it. That's known as geminate recombination. But roughly speaking, we can say that if we divide this Q value by the average energy, we get something like 100,000 primary electrons and 100,000, exactly the same number of primary ions. Okay? So the question is, what are the fluctuations that we get? And that can be described through this. So we would expect that this might be the square root of that, but instead it's this slightly different formula where the fluctuation is given as the Fano factor times this n, which is this, and that can also be given this way. And you get a number like 124 electrons. So the intrinsic fluctuation is a little bit more than 1 part per thousand in the xenon. That's not bad. That's quite intriguing. But does anybody know what this Fano factor is? Has anybody ever heard of that? Fano factor? Anybody? It was conceived by a theorist, so it has to be right. The Fano factor is very interesting, and I want to take a few minutes to discuss it. It expresses a constraint that occurs when you put, for example, a fixed amount of energy into something like xenon gas. Let's imagine it's this cesium gamma ray, which is precisely 662 keV. And if it takes a fixed amount of energy to create an electron-ion pair, let's imagine for a moment that it takes exactly, instead of 25 electron volts, it takes exactly 24.57 electron volts. Then we would get exactly 100,000 primary electrons with no fluctuations, right? I'm hypothesizing that the energy loss goes into a process that takes exactly 24.57 electron volts to produce an ion pair. This is not exactly right, of course. But in that case, we would get 100,000 plus or minus 1, maybe. So the central idea here is that there's a process which is somehow quantized. It takes a certain amount of energy to produce something. Now this 25 electron volts is more than the ionization potential of xenon. I think I mentioned that number the other day. It's 12 volts. And I also mentioned, I think, the excitation energy of xenon, which is 8. So if you add those two up, that's only 20. And there's a few more electron volts left over. What could that be? What about those other few electron volts between 25 and 20? that energy is what's given to what's known as sub-excitation electrons. Those are the electrons that don't have enough energy to excite the xenon. They just rattle around until they lose their energy in thermal energies by collision. An electron colliding with xenon loses about 1 part in 100,000. So it takes a long time. But anyway, that's where that energy goes. So we see that there's 3 processes here, not just the one that I hypothesized. There's ionization, there's scintillation, and then there's these sub-excitation electrons. So we don't have this situation where there's going to be exactly 100,000 primary electrons, plus or minus 1. There's 3 processes here, and so there's fluctuations between them. And most of the energy goes into ionization, but some goes into scintillation, and the fluctuations between those 2 channels determine what you get. And it's this Fano factor, which is less than 1 in the case of gas, that gives you a boost here. Otherwise, it would be the square root of 100,000, which is like 300. So nature is giving us something here. So this is an important conceptual thing to understand. The fluctuations are not just the square root of that, but they're reduced by the fact that there's quantization processes going on that are not exact, but they do introduce an effect that reduces the overall fluctuation in the electrons. Okay, so this is what the Fano factor is doing for us. It's reducing the amount of fluctuation. So if we calculate what the energy resolution, the intrinsic and the gas phase, it's only 0.3% full width for the ionization signal only. That's really appealing. Now how would we should compare this to the germanium diodes, which are the champions of energy resolution? They actually have the same Fano factor, germanium as a material, as xenon. However, the energy to produce an electron hole pair in germanium is only 3 electron volts. So they have a factor 8 more of the primary ionization excitation carriers, so they can get another factor of almost 10 in the square root here. So they go down to 0.1% as their intrinsic resolution. But this is not bad. How are we going to preserve this in a real detector? Okay. Before I get there, let me mention one other thing that you can get in the xenon gas. You can actually see these events. They're about yay long in xenon of 10 atmospheres. So a real 2-electron decay will scatter around because xenon is prone to a lot of multiple scattering. And as the electrons run out of energy, they scatter around and they produce kind of a blob. So the true events look like spaghetti with 2 meatballs, where the gamma ray induced events typically don't have their high energy when they start, and they only have 1 blob or 1 meatball at the end. So that is a powerful constraint that if you could actually work with Monte Carlo truth, you'd get a factor of 100 reduction relative to assuming or concluding that background events were really true. But in practice, because of diffusion and instrumental effects, we don't get that factor of 100, but more like a factor of 10. Okay, so the takeaway with xenon is that in principle you can get really great energy resolution using only the ionization information. And as you saw, it's easy to drift all of the electrons down to some readout plane, whereas it's hard to get most of the photons. You can typically only capture a few % of the photons. Okay, and we can also get some topological information because gamma rays also Compton scatter and produce complicated events that we can identify as well. So the next experiment consists of a TPC with an active volume, a cathode to establish an electric field that drives the electrons down to this blue region, which is an electroluminescent region where light is generated, which is detected by a plane of silicon photomultipliers